All right, guys, in this video, we're going to talk about section 3.2, exponential functions. We're going to break this one apart into two videos, just like we tend to do these days. Well, the first thing we need to talk about is what the structure of an exponential function is, and that's what you're seeing on your screen. Your function f for an exponential is going to kind of match this type of setup where you have a number, we're going to say a, times some number written to a power. Now, this first number that you're seeing, that is your initial value. That's the starting point. The number that's being raised to a power is going to be a constant. So you got to make sure that you're looking out for that. Both a and b, these values, the initial and that base, are going to be constants, while your exponent is a variable. Couple things to look out for as well. We want to be able to tell if we have exponential growth or exponential decay. Exponential growth will be when that b value is more than 1. We will have decay if that b value is between 0 and 1. So always just look out for that as well, okay? All right, so here we have first example. They're asking, is it exponential function, and explain. So what we're going to be doing with this is determining if it's exponential based on the kind of like pattern that we've set up. And if so, cool, explain why. If not, explain why, right? What we have here for the first one is we have just f of x equals 3 raised to the x power. And so a lot of people have looked at this and they said that they did not believe that it looks like an exponential function. Here's the problem. We do have a constant raised to a variable, but what some people have pointed out is that they did not see an a value. Here's the thing, guys. If you don't see an a value, it's okay. It just means that that a is automatically like a little invisible one that you're not seeing. Okay, so this is considered an exponential function. The a value just would be 1. So I'm going to say, yes, it is. The a value is 1. That's the initial value. We're just not seeing it. Okay, the b value is 3. That's the base. All right, and the other reason we know that this is exponential is because my exponent was x. Okay, those are the components we need. We need the a and b to be constants, and we need my exponent to be x. Okay, so look at part B. This one says 6 times x to the negative 4. So I want you to look at this. Okay, do you see how the exponent is not a variable? The exponent is a negative 4. B is not a constant. B is x. So there's a couple things that are wrong with this. It's not an exponential function, and that's because basically we can just say x is not the exponent. Yeah? This last one on part C, we have 7 times 2 raised to the negative x. Now, this one's a little bit more tricky to like justify. A lot of people look at this and they say that negative is a problem. Well, the negative does do something weird. Okay, so I will give you that. We need to talk about what the negative exponent does. Really, this is saying 2 to the negative first to the x. Well, a negative power turns this into a 1/2. Okay, so this is actually still a exponential function. It's just that the base, is a fraction, and that's okay. It makes us have exponential decay. So that's really the issue with it. But it's still an exponential function, so we're going to say yes. Okay, that a value is 7. The b value is actually 1/2. And we know our exponent is x. Okay. All right, next thing. We got this example 2 down here. They said to evaluate the following. And yes, I'm sure you could just type it in your calculator and get an answer, but we're not going to leave it that simple. We're definitely going to make sure that we can do this by hand. It is 100% possible. Okay, so we're going to go through these, working through it by hand. If you would like to pause the video, try it, and then come back when you're done, feel free to do that. Okay. So we have this first one. We're going to plug in f of 4. And to do that, we're just going to replace x with f4. So this becomes 2 to the 4th 2 to the 4th power, 2 times 2 times 2 times 2 is 16. Look at this one over here. F of 0. We're going to plug that in. 2 to the 0 power. Well, guys, anything to the 0 power is simply a 1. There we go. This one's the one that's a little weirder, okay? A little bit more wild. And depending on what calculator you're using, if you typed it in, it might give you all kinds of different things. So I'm going to show you what we could do by hand, okay? We have f of negative 3 halves, and that is 2 raised to the negative 3 halves power, okay? First things first, negative exponents make us have a fraction, okay? So really, this is to the 3 halves power like that, okay? 1 to any power is always going to be 1, so I'm not worried about that. But 2 to the 3 halves is a little bit more tricky maybe, okay? So what we're going to do here is actually work through this. When you have a fractional power, the denominator becomes the index of a root. So we're going to have 1 in the numerator, and then the denominator of this exponent becomes the index of a radical. So we get the square root of 2 raised to that numerator power, so to the 3rd power. Not sure if y'all can see this very well. It's pretty little. Let's see if we can do that a little bit better. All right, so we have 1 over the square root of 2 cubed. Well, the square root 2 cubed, there we go, 1 over the square root of 8. Now I can simplify this. This becomes 1 over the 2 square root of 2. But the problem is we don't like this as an answer, okay? So this is okay for some people, and it may even be okay on the AP test, but certain calculators will not have put it in this answer. So just kind of depending on what calculator you're using, you may or may not have gotten this exact same thing. What we like to do is not keep radicals in the denominator, which would mean that you got to rationalize it. And I could multiply square root of 2, top and bottom, to rationalize that guy. It would leave us with square root of 2 over square root of 2 times square root of 2 is square root of 4, which is 2. That times that 2 in the front gives us a 4 in the bottom. So all that work to give you this value. If you got it as a decimal, it's about 0.354. So that's also a valid answer, depending on how they want it, okay? So I know that's a little bit more tricky to do by hand, but it is manageable, okay? All right, example 3, we're going to talk about transformations for just a moment. So example 3 brings us to transforming exponential functions. It's working basically the same way that transformations have worked in the past, okay? So I don't want you to overthink it too much. This says to describe the transformation from f of x equals 2 to the x power. We have this first one, g of x equals 2 to the x minus 1. All right, let's talk about that transformation for just a moment. 2 to the x minus 1. Now, remember that whenever you have the transformation happening 2x, right, where it's changing the input, that is a horizontal type of transformation. So I see this number as being subtracted from x in that exponent. That is a horizontal transformation. And because it's an adding or subtracting value, this is a translation, a shift. Okay, so we're going to say shift. And horizontal stuff is always backwards from how we think. This is shift to the right 1. The next one says we have 2 to the negative x. All right, well, y'all look at where that negative is. So many people will tell me that it is a reflection, but what kind of reflection, you may ask? That's a good question. So keep in mind, when you change the input, this changes things horizontally. Which type of reflection changes things horizontally? Well, think about it. If I take something and I reflect it across the x-axis, right? If I took a parabola, pretend my hand looks like a parabola, and I reflect it across the x-axis, it would end up upside down, right? It doesn't actually change your y or x values. It only changes the y's. It doesn't change the input. It only changes the output. This is changing the input. Okay, it's changing your x values. So it's the same as if I had something. Sorry, I can't mime with my hands very well under the camera. If I had something, say I had a parabola and I reflected across the y-axis, it would reflect kind of that way, right? So your input is what ends up changing when you reflect across the y. Basically, if your negative is with the x, you've reflected across the y. If your negative was in front of the function, you've reflected across the x. This one's with the x, so we reflect across the y. It's almost kind of backwards in what it feels like. This is the y-axis. All right, this last one, we have a number that's being multiplied times 2 to the x, and that right there is a vertical dilation. And we're going to say, remember, vertical dilations, you don't have to do anything weird. It's just by 3. Okay, so just vertical dilation of 3. All right, y'all. So what we're going to do here is pause the video, or we're going to pause the lesson, and I'm going to break. In the next video, we are going to talk about the other bit that you're seeing down there. You're seeing stuff about E. We will discuss that in the next video, okay? But that is it for this first part, and I will see y'all in the next one. Bye.